Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will review everything you need to know about probability for your upcoming test. So probability is the assigning to random events a number between and including 0 and 1 to indicate how likely it is to occur. So I'm going to ask in the test for the probability that something happens, and you respond with a number. That number has to be between 0 and 1, can be 0, can be 1. So the number that you give tells us if the event is likely, unlikely, or whatever. So events that have probability close to 0 are unlikely, close to 1 they are likely. So how we actually calculate the probability of an event is using this formula here. This says probability of an event is the number of ways it can occur over the total number of outcomes. Note we use S here because this means the number of outcomes in the sample space. Now you can only use this formula when each outcome is equally likely. So let's look at an example. Suppose that I roll a normal 6-sided die. So what I'm going to do is write the sample space. I use these squiggly brackets to indicate a set. We have here a set of outcomes. There are 6 possible outcomes if you roll a normal 6-sided die. Each of these outcomes is equally likely. So the probability that I roll a multiple of 3, there are 2 ways that it can occur. I can get a 3 or a 6 out of 6 outcomes in total. So the probability here is just 2 over 6. Now when you write probability, it can be a fraction, decimal, percentage, doesn't matter. Just make sure that your fraction, if you write it as such, is simplified. So the probability of an even number, again, I just count how many ways can that occur. Well, I can get a 2, a 4, or a 6. There are 3 ways it can occur out of 6 outcomes in total. I'm going to simplify my fraction. Now again, you can write it as a decimal or a percentage, it doesn't matter. Just make sure you remember every time you're asked for a probability, the answer has to be between 0 and 1, can't be more than 1, can't be less than 0. So let's go and find the probability. I roll a number that's even and a multiple of 3. So and in probability means it has to be both. It has to be even, it has to be a multiple of 3. So from our sample space, 6 is the only number that is both even and a multiple of 3. There is only one way this can occur out of 6 outcomes in total. So what about the probability that it's even or a multiple of 3? So or sometimes causes a bit of confusion. What it really means is it can be even, a multiple of 3, or both. So to count the number of ways this can occur, I include all of the even numbers, all of the multiples of 3. I don't include 6 twice though. So there are 1, 2, 3, 4 ways that this can occur out of 6 outcomes in total. So it's 4 over 6. Simplifies to 2 over 3. All right, what's the probability that it's even or a multiple of 3 but not both? Well, I still have these outcomes, except this time I'm not going to include 6 because 6 is both even and a multiple of 3. And the question said don't include both. So I'm left with 3 possible outcomes out of 6 in total, which simplifies to a half. All right, let's now look at complementary events. So if we have some random event here, A can be like tossing a heads, rolling a 3, etc. It can be any random event we like. So A is the event. We write A complement like this with this little dash. It basically means not A. This formula says the probability an event does not happen is 1 minus the probability it does happen. Now, it might be a bit technical to look at it like this, but really this is commonsensical. You know that if there's an 80% chance of rain tomorrow, that means there's a 20% chance it won't rain, because percentages have to add to 100. In the same way, probabilities need to add to 1. So, if the probability I attain an A in maths is 0.78, the probability I don't attain an A is just 1 minus 0.78, which is 0.22. If there's a 78% chance I do score an A, there's a 22% chance I don't, because probabilities have to add to 1. So attain an A and don't attain an A, they are complementary events. Complementary events are just an event and not that event. Get an A, don't attain an A. So note here that attaining a B is not the complement of attaining an A. The reason is if you don't get an A, that is not the same as getting a B, because you could get a C, a D, or whatever. So because these two events are not complements, we actually can't figure out this probability from the information given. I just wanted to make the point because a lot of people would think these are complementary events, but they're not. Complementary events, they have probabilities that add to 1. Two events are complementary if one event is the same as the other not happening. So because these two events are not complementary, their probabilities need not add to 1. We can only use this formula here when we have an event and its complement. All right, let's now take a look at Venn diagrams and two-way tables. So Venn diagrams and two-way tables are used when we have questions involving multiple sets. So the whole point of them is to display the information, how many are in each set, in a convenient way so that we can answer probability questions easier. Now, two-way tables and Venn diagrams do exactly the same thing. They're used for the exact same purpose. So let's look at a question. 26 people in a class, 16 drink Coke, 8 drink Pepsi, 7 drink neither Coke nor Pepsi. So we can arrange this in either a two-way table or a Venn diagram. So for a two-way table, there are 4 rows and 4 columns. There's 2 ways you can be in this question. You can either be in set C or not C. You can either be in set P or not set P. So these are all the people that drink Coke, don't drink Coke. These people drink Pepsi, these don't drink Pepsi. So we have 4 options here and we'll populate these with numbers. Now, you might be wondering, well, hang on, 16 plus 8 plus 7 is 31. How is it possible when there's only 26 people in the class? Well, however many you've overcounted is how many are in both. So because we've counted up to 31, we've overcounted by 5. The only way this is possible is if I counted 5 people in the set of people who drink Coke and again in the set of people who drink Pepsi. So we've overcounted by 5. 5 are in both. This is where both are because they're in the Coke column and the Pepsi row. We're also told here that 16 drink Coke, so in a two-way table, always this last row is total, this last column is total. We're also told in the question that 8 people drink Pepsi, so I'll put an 8 here. That's the total of the Pepsi drinkers, and our total should add up to 26 because there are 26 people in the class. So we now have enough information to fill out the rest of this two-way table. This number here is saying, what do you add to 5 to get to 8? It has to be 3. And similarly, 11 go here, 18, 7, 10. So we could have just as easily displayed this information in a Venn diagram. For a Venn diagram, you always have a rectangle and 2 circles inside. The 2 circles are for the 2 sets. So here the sets are people who drink Coke, people who drink Pepsi. So the 5 who drink both go in the middle. Over here, we have 11 people that drink Coke but not Pepsi. We have 3 people that drink Pepsi but not Coke, and 7 that drink neither. Notice that the 4 numbers here in the two-way table are the same as the 4 numbers in the Venn diagram because they display the exact same information. So once we've done this, we can answer probability questions really easily. So let's look at probability of C. That means if I select a student at random from this class, what's the probability they drink Coke? Well, we can see here there are 16 people, 11 plus 5, who drink Coke out of 26 people in total. Make sure if you give your answer as a fraction, it is simplified. So this says the probability of not P. The probability if I pick someone at random, they don't drink Pepsi. So we can see from the two-way table there are 18 people who don't drink Pepsi. These 11 and these 7 don't drink Pepsi, so there are 18 such choices out of 26. Once again, I'm going to simplify the fraction. So just note this symbol here means and. So this is saying the probability if I pick someone at random, they drink Coke and Pepsi. So that's these 5 people here. There are 5 people who drink both out of 26 in total. So make sure you know that this symbol means and this symbol means or, because people often get confused about this. So when you're doing an and question, you usually have to get one number from the Venn diagram or two-way table like we just did. When you're doing an or question, so this is the people who drink Coke or Pepsi, you have to get 3 numbers. So what we want to do is we want to include everyone who drinks Coke, everyone who drinks Pepsi, everyone who drinks Coke, everyone who drinks Pepsi. And whenever you see this symbol, we do include those in both sets. So from either the Venn diagram or two-way table, 11 plus 5 plus 3 is 19. There are 19 out of 26 in the class who drink Coke, Pepsi, or both. This here says the probability someone drinks Coke or they don't drink Pepsi. Now, as I said before, if you're doing an or question, you need to get 3 numbers from the Venn diagram or two-way table. So we want to include all of the people here that drink Coke. So we want to include those 16, but also these 7 because they don't drink Pepsi. We include these because they drink Coke and this one because they don't drink Pepsi. So 11 plus 5 plus 7 gives us 23 out of 26. So for this final question, we have the probability of P given C. So that means if I choose someone at random who I know drinks Coke, what's the probability they also drink Pepsi? So this given C means I know I'm in the C circle. I know I'm restricting myself to only these 16 Coke drinkers. So there are 16 Coke drinkers to choose from. Of the 16 Coke drinkers, 5 of them, these 5 here, drink Pepsi. So it's 5 over 16. All right, let's look now at a harder Venn diagram question. So here we're given a Venn diagram. We're told probability of A is 1 over 6, and we will now find X. So the probability of A is everything in A. Now, a lot of people say, oh, there's just 2 in A. No, there's not. There's actually these 2 you need to add together. So there are 5 in A. So the number of choices we have is 5. The total number of choices is 14 plus 3 plus 2 plus X. It's 19 plus whatever X is. So 5 over 19 plus X equals 1 over 6. So let's go through and solve this equation. We learned how to solve these earlier in the year. What you do is cross multiply that by that, that by that. So I go 5 times 6 is 30. 1 times 19 plus X, well, that's just 19 plus X. So now I'm just going to subtract 19 from both sides. I get 11 equals X. 11 goes here because then we will have probability of A is 5 over 30, which is 1 over 6. All right, let's now look at multi-stage events. So when we have multi-stage events, we use tree diagrams or tables. So this is a multi-stage event. Say I have a red, a blue, and a green marble. You're randomly picking 2 of those marbles. Calculate the probability of picking blue or green, but not both, if it's done with replacement. Now, with replacement here means that if you pick, say, a blue, it's replaced by another blue. It means that you can actually get 2 blue, 2 green, or 2 red. Now, when we're solving a question like this, we use a tree diagram or a table because this is a multi-stage event. It is an event that occurs in stages. Basically, you're doing 2 things here. You're picking first marble, then picking a second marble. So whereas Venn diagrams and two-way tables are used when you have 2 sets in the question, we use tree diagrams or tables when you have 2 stages, when you're doing 2 things. So the table we use here is different to a two-way table. In both cases, the table or the tree diagram, the only purpose of it is to list all the possible outcomes and thereby make probability calculations easier. So let's start by drawing up a table. So what we're going to do across the top is we're going to list the possible outcomes of the first marble that's picked. So the first marble that's picked can be red, blue, or green. Now down the side, we're going to list the outcomes of the second marble being picked. Because we can pick the same marble twice, because it's with replacement, the options are red, blue, and green. So in this space here, we're going to list all the possible outcomes. So this is, you can get a red first, then a red second, blue, then red. You can get a green, then a red, and so on. So here is my list of all the 9 outcomes. Now we could just as easily have used a tree diagram. This is how a tree diagram works. You list all of the possible outcomes for the first stage, in this case, the first pick of the marble, which was red, blue, or green, and you draw branches to each of them. If I get a red first go, I can get a red, blue, or green second go. If I get a blue first go, I can get red, blue, or green second go, and so on. So what I do now is over here, I'm going to list each of the possible outcomes. I get them by following the branches. So red, then red, that's our first outcome. Our next outcome, I follow the branches, red, then blue, and so on. So you can see here, this list of outcomes is exactly the same as in here. It doesn't matter which you use, the tree diagram or the table, because the point of it was just to list all of the outcomes. We've done that here in black, here in blue. Now that makes the probability question far easier. We're going to calculate the probability of picking blue or green, but not both. So because each of these outcomes here and here is equally likely, all I need to do is go and highlight the ones that are of interest. So I want the probability of picking blue or green, but not both. So that's this one because it has blue. It's this one because it has green. This one has blue, this one has blue, this one has green, this one has green. Note, because it said but not both, I don't include these ones. So that's really easy. We can see that we've highlighted 6 out of the 9 outcomes. We could have just as easily done it in the table. We would have included these ones. We don't want to include the B and G ones because it said but not both. So in either case, we've highlighted 6 outcomes out of 9 in total. So that's our final probability, which is 2/3. So how would this change if it was done without replacement? Let's now look at that. So we're looking here at the same questions on the previous slide, but this time the marbles are picked without replacement. What that means is if you say pick a red, you can't pick it the second go because it's not replaced. You can't get 2 reds, 2 blues, or 2 greens. So I can still use a table or a tree diagram to list the outcomes because this is a multi-stage event. You're still picking 2 marbles. But here I'm going to put a cross through these cells because I can't get 2 reds, 2 blues, or 2 greens. But otherwise, the process is the same. I simply write the list of possible outcomes. So I have green, red, blue, red, and so on. And for my tree diagram, I have red, green, blue. But if I pick a red first go, I can't get red the second go. I can only get green or blue. If I get green, I can only get red or blue on the next go. And of course, if I get blue, I can only get red or green. So once again, I still follow the branches to list the outcomes, red, green, red, blue, and so on. And so you can see that there are 6 equally likely outcomes this time. There's fewer outcomes. So the probability that I pick blue or green but not both. So highlighting the outcomes that satisfy this, I can see I've got a green here, blue here, green, blue, but I don't want to include the ones that are both. So I've got these ones here, but I don't want to include the ones that are both. So out of 6 equally likely outcomes, there are 4 that have a blue or a green but not both, and that simplifies once again to 2/3. All right, thank you so much for tuning into this video. Best of luck studying for the test, but you'll ace it. You're a star. This has been the luckiest maths teacher in the world. Have a great day.